Hello everyone, this is your tutor AB. Today we're going to be solving a problem from the IB Physics HL May 2024 examinations. This is a paper 2 problem. Let's get started. At a distance r from the center of a planet, the gravitational potential due to the planet is Vg and the gravitational field strength is G. Show that Vg is equal to negative Gr. Now, Vg, your gravitational potential, that is a formula given in your formula booklet. This is nothing but Vg is equal to negative Gm over r. Now this is in the data booklet. Now another equation given in the data booklet is the equation for the gravitational field strength, G. G is equal to positive Gm over r square. Now I want you to just take a look at these two expressions. Are they not really similar? Well, yes, they are. The only difference is that G just has an r square on the bottom, whereas Vg has just an r. So we can manipulate these two expressions to give us what we need. So I can say Vg is basically just negative 1, because that's the negative sign that I need, Gm over r square times by r, correct? Because this r square and r would cancel, I'll be left with just negative Gm over r at the bottom. So, and we know that Gm over r square is just G. So this is just G. So I can say that Vg is equal to negative Gr. Okay, next question. For Earth, the variation Vg with r is shown. So here they've given us a graph, and if they give you a graph, most likely you have to actually use it. So a satellite of mass 750 kg orbits the Earth in a circular orbit of radius 10 to the power of 7 meters. Calculate the magnitude of the gravitational field strength at the orbital radius of this satellite. Okay, now what is the orbital radius of the satellite? Well, before we do anything, what is the equation for the gravitational field strength? We know the gravitational field strength is equal to Gm over r square. Okay, but in this question we don't need to use it. Why? Well, take a look here. They've given us a question at an expression at the very start of the question, meaning we probably can use it later on in the question, and in this case we can use it, and I'll show you how. So leave this equation, okay, and use what they've given you. Vg is equal to negative Gr. So G is what I want to solve for. So I can basically say negative Vg over r is equal to the gravitational field strength. Now, what is the gravitational potential at the point that they want? 10 to the power of 7. So if I just check, the orbital radius at this point is approximately negative 4 into 10 to the power of 7 joules per kilogram. So I can say negative 4 into 10 to the power of 7, and this is over the orbital radius, and the orbital radius is 10 to the power of 7. So I just use whatever they given me, looked at the graph, and got the data points that I need. That's 10 to the power of 7. So that's equal to G. So G is basically equal to this becomes a positive, these two cancel, and so 4 meter per second square, because this is basically just gravitational acceleration. And that's the answer for this question. Next, the gravitational force acting on the satellite. Now, what is the equation for the gravitational force? F is equal to Gmm over r square. Now, did we not calculate this term right there? Because what do we know? G is equal to Gm over r square. And I calculated that right here. I calculated G earlier. So I can basically say F is equal to G times by m of the mass of the satellite. Okay, so F is basically equal to G 4 times 750, and that's basically, put this in your calculator, 3,000 newtons. Okay, now part C. The satellite is moved to a new circular orbit. It's a new orbit. The orbital radius of the satellite increases by 2 kilometers. Outline why the magnitude of gravitational field strength at the new orbit is approximately the same as the old orbit. Okay, think about it this way. What was the radius? What was the orbital radius? The orbital radius was at the beginning 1 into 10 to the power of 7 meters. Now that's a big number. And what does it increase by? It increases by just 2000 meters. Let's just convert that. So that increases by 2000 meters. Now if you compare these two, the increase, so the new orbital radius, if I say that's the old and that's the new orbital radius is just 2000, 10 to the power of 7 plus 2000. Now if I make a comparison between these two values, it's really basically the same, right? Because the number was so big to begin with, adding 2000 meters isn't really going to make much of a difference to your gravitational field strength. And so that's your answer. The reason it stays the same because the orbital radius change is not very significant, right? Because the number itself is not that much different. And we can basically use the equation to back this up. Now, what is the equation for gravitational field strength? We can just say that's positive gm over, and we can just say in here 1 upon the change in the radius, right? Change in the radius, the whole square. So, like, if you look at this, there's not going to be much change. And the change in the radius is inversely proportional. I'll just say it like this. Change in the radius is inversely proportional. I'll just say it the other way. G is inversely proportional to the change in the radius. And so because the radius hardly changes, G will hardly change. And so that's why it stays the same. Now, that explanation was not the best. So if you have any questions, leave it in the comments and I'll answer it better. But I think this is the general gist of it. The idea is that there's barely a change in radius because 2000 meters is not much, and because g and r square are inversely proportional, because r square doesn't change much, g doesn't change much. Okay, now finally, determine the change in the total orbital energy of the satellite. Now, okay, let's derive an expression for the orbital energy of a satellite. And now you don't need to do this, but I will do it because it makes these type of problems a lot easier. Rather than having to do so many extra steps, we can just memorize this formula. Now I'll derive this formula for you, and then afterwards just keep it in your head and use it whenever necessary. So we can say the total orbital energy is basically equal to the potential energy, the gravitational potential energy, which is given in your data booklet, which is negative gmm over r, plus the kinetic energy. Now, the kinetic energy is just half mv square of the object in the orbital radius. Now, the thing is, it's just not just any v, it is the orbital velocity. So instead of v, we can plug in the formula for the orbital velocity. Now, in your data booklet, orbital velocity is given as gm over r. That is your orbital velocity. So basically, if I were to simplify this expression, I'd get negative gmm over r plus gmm over 2r. Now, if I were to make a common denominator, I would simply get the expression for the total energy to be gmm over 2r. Now, this is a very important expression for total energy, gravitational energy. So remember this, total gravitational energy. You don't need to do this proof every time. Just remember this, and that'll make your life a lot easier. Okay. So, plugging into this expression will give me the change in the orbital radius. So, in this case, the delta ET is just gmm over 2 times by 1 minus and the change in the radius. So what's the change in the radius? So is the radius initial minus the radius 1 over the radius final. Okay, this is basically the expression I want to plug in all my numbers to. And when I do this, because what does this represent? This just represents a delta R. So when I plug in my numbers into this expression right here, I'll be able to get my change in energy. Okay, so let's plug it in. Delta ET is basically equal to, now what is the gravitational constant? It's given in a formula booklet. It's 6167 into 10 to the power of negative 11, and that divided by 2 times by, what's the mass? What's the mass of the planet? That we need to find, but we do know the mass of the satellite. So we know the mass of the satellite is 750 kilograms, which they gave right here. And now we need to find out the mass of the planet. So how do we do that? Well, to find the mass of the planet, this is what we can do. Before we go further, we'll find out what's the mass of the planet. So the mass of the planet, we know that Vg is basically equal to negative gm over r, correct? Now we know the gravitational potential at a certain point, which we calculated here, is basically just 10 to the power of 7. That's the negative 4 into 10 to the power of 7. That's the gravitational potential at this orbital radius right there. So using some constant values from the graph, we can basically find out what is the mass of the planet. So the gravitational potential at the orbital radius 10 to the power of 7 is just negative 4 into 10 to the power of 7 is equal to negative 6.67 into 10 to the power of negative 11 times by m, which is what I want to solve for, over the orbital radius, which is 10 to the power of 7. Now, no matter which point you use on the graph, the final answer will be the same. Okay, so you'll basically get, negatives will cancel out, 4 into 10 to the power of 14 over 6.67 into 10 to the power of 11. That will give me the mass of the planet. So the mass of the planet, if I put this into the calculator, gives me what? 10 to the power of 14 over 6.67 into 10 to the power of negative 11. That gives me approximately 6 into 10 to the power of 24 kilograms. So now that's the mass of the planet, which I'll substitute into this expression right here. So we don't need to, we know what it is now. It's 6 into 10 to the power of 24. Okay, we got this, we got this. And now we need to basically find out what is the change in the radius. So what was the initial radius? The initial orbital radius was 10 to the power of 7 right here. And now minus 1 over, and what is the new radius? The new radius is basically the old radius plus an additional 2000 meters, right? Kilometers to meters, 2000. So now, if I were to put this expression in the calculator, I'll be able to get what is the change in the total gravitational energy. So let's check it out. What is it when I put in the calculator? Times by 750 times by 10 to the power of 24. Okay, 1 over 10 to the power of 7 minus 1 over 10 to the power of 7 plus 2000. Now I get, the answer comes out to be 3 into 10 to the power of 1, 2, 3, 4, 5, 6. 10 to the power of 6 joules per kilogram. Okay, thank you for watching. Please like and subscribe. If you have any oh no, not joules per kilogram, just joules, sorry. Thank you for watching. Please like and subscribe. If you have any questions, leave it down below and I'll answer it as soon as possible. Thank you for watching.